Thank you. Oh. Is this on?
Yeah.
I think now it's on? Okay. All right. So, as you see, today I'm changing gears and I'm going to talk about flows, so time-dependent problems. So here is a plan, rather ambitious. I hope I can make it to the end. I plan to start with some basic material, probably known for many of you, and then some applications. The discussion will be rather abstract at the beginning. There will be examples later, and some new developments on space discretization, and particular on applications to TV flow. You will see as we go through. Okay, so here's the background. As I said, it will be a bit abstract at the beginning. So let's say that we denote by H is Hilbert space. A functional on that Hilbert space will be denoted by phi. Let's say it will be lower semi-continuous and convex. The domain will be denoted by d of phi. Then this potential has a subdifferential, which is a map. I call it cal f, with these properties, typical of a subdifferential. Okay, so the picture you have to keep in mind is that the function phi is like this, is convex, and so this is a point, let's say W, and this is a point B, and we are approximating with the tangent, which is f of W times V minus W. This is exactly this quantity. And we want to compare with phi of V minus phi of W. And that's what is written in this inequality. Okay, so that's a general situation. And of course, this implies monotonicity, which is written here. So that's a basic background. So allow me for a moment to continue without giving examples. I'll come to the examples in a second. So this goes back to the 70s, when the early 70s, when the semi-group theory was developed. So you have the concept of strong solution, which I wrote here. In particular, in this Hilbert space, we are going to assume that the function u is absolutely continuous, so this derivative makes sense almost everywhere. If you multiply this equation by u minus v, v being a test function in the domain of the operator, you get, because of this relation here, you get a variational inequality, which is written in this way in terms of the function phi, which is going to be essential for the discussion. Multiplying this equation formally by u prime, you get this formula, u prime in the norm of the Hilbert space, which I write with 1 bar square, and formally here you get the subdifferential derivative of phi of u times u prime, which you can write in terms of the chain rule. Of course, it requires proof, as the derivative of time of phi of u. And then you have the product of f times u prime on the right hand side. So this identity will be essential. And there is another inequality, dissipation inequality, that you get by formal differentiation of the equation and multiplication by a proper test function, so you get this. That requires more regularity, as you see on F. So that's a sort of basic background. And here are examples. So the first one, which is a recurrent theme now in the context of parabolic equations, is the obstacle problem. So again, we have a convex set with an obstacle that I call psi. This is the energy defined on this space L2, which is the usual Dirichlet integral plus the indicator function of a convex set. So the indicator function is infinite for functions that are not in the convex set, and that enforces that the solutions of the equation have to belong to the convex set. So here is the variational inequality in red that you will get using the approach that I mentioned earlier. Similar to what we discussed yesterday, except that yesterday we didn't have the time-dependent part. Okay, so this is a very classical example, very well known. But it appears in applications, even recent applications in phase transitions, but not that recent, maybe in the mid-90s, more recent in finance, and so on. So this is one of the prototypical examples. Connected to Benoit's talk, you have the general diffusion, in particular, as you see here, the equation, the Stefan problem, or even porous median equation, depending on what beta is. And here you have a background. The functional space is H minus 1, which you can define the norms in terms of the inverse of the Laplace operator. And then the functional is defined as in terms of an antiderivative of beta, beta being this function that was defined earlier today. Let me plot it again here. Beta would be something like this. Okay, this would be the latent heat for the Stefan problem, and then you end up with this subdifferential, and in particular, this is the equation. And the third example that I got involved more recently is a total variation flow. In this case, I got involved because of applications of this equation as a component in equations in material science. But it's certainly a type of function that appears in other areas, for instance, image processing. So now we have the total variation, which I wrote as an integral, using a little bit of notation. So you need to assume that the functions are dV, and that would be the total variation. And formally, the derivative of this, if you formally compute, is this operator. The formal subdifferential is the divergence of grad u over mod grad u, which is a very singular object. Particularly, it's not very clear what it means when grad u is 0. If you have a flat part, something that will be important in the discussion that follows. There is a characterization of the subdifferential, which is very rich, the subdifferential of this operator. And in particular, you see here, I define a space that will be important later, capital X, that L infinity vector fields with divergence in L2, proper boundary condition, Neumann condition, and then the ball in this space, I call it B1. Then for an element div Z to be in the subdifferential means that Z is in the unit ball and it satisfies this relation. This relation in terms can be written as a variational inequality. It's written here in red. Okay, so if you want to enforce this, you can instead write a variational inequality that links all this discussion to the previous talks. So this equation can be written as a couple of equations where the Z here appears as such, and then an equation that tells us that the divergence of Z is in the subdifferential of phi of the functional phi of E. So this is the way I'm going to think about the problem, okay, as a system. But it's within the framework that I discussed earlier. Okay. It's possible to define coercivity in this context, and by coercivity I mean a measure of the deviation of this convex function from the linear approximation. This can be made quantitative through a quantity that I call sigma, or a corresponding rho, and you can rewrite the variational inequalities adding that term. This is a refined form of the variational inequality, but I'm not going to emphasize this. Okay, I just wanted to say that I'm going to go for the minimal theory, the simplest theory. This is possible, and it will leads to interesting terms, energy terms, when you do the analysis. But I will not emphasize that. So let me go to subgradient operators. So again, here I wrote the equation that I'm going to be looking at, and I took the right-hand side equal to 0. Again, for simplicity, And I'm assuming that this function f, this map, is again is a subdifferential of a convex functional. And I wrote again the energy identity that I discussed earlier. Here is the variational inequality. And the purpose of this talk, at least at the beginning, is to discuss how well this approximation does. So here, the u prime is replaced by a difference quotient. Tau n is a time step. And then the phis are replaced by corresponding objects. So this is a discretization in time, a Backwell-Euler method, the simplest possible method for that equation. Okay, so at the beginning in this discussion, I'm thinking of this problem, which is in general defined in space and time, viewing only the discretization in time. Then I will come back to the discretization in space. And the question is, what can we say about the difference between un and u, a small u? Okay, so this is a very classical question that goes back to the 70s. It was addressed by a fundamental famous paper by Crandall and Liggett in the context of semi-group theory in Banach spaces. It's a very mysterious type of result, combinatoric in nature, to some extent difficult to understand. What they show is that if you have a uniform time step, the error between this u and this u in the L infinity norm measured in the norm of the Hilbert space H is square root of tau. This is an a priori result in the spirit of what I mentioned yesterday. What I want to do today is twofold, at least at the beginning. I want to give you an a posteriori theory, which is based on this quantity, which is I call numerical dissipation, which if you look at this formula, and you take here v equal un minus 1, which is an admissible test function, you get it directly from here by dividing by tau n. Okay? So if you replace capital V by un minus 1 and divide by tau n, you get this. And the sign is coming directly from this formula. So I'm going to use the negative of this quantity, which I call E sub n, as a measure of the error. Notice that this is a discretization of that. In the limit, we expect this to be 0. But for a discretization, there is an inequality. And the difference between, well, the fact that this is not necessarily 0 is a measure of how well this un is approximating the u. And I'm going to use this numerical dissipation to compute the error. And at the end of the day, I'm going to show you that provided we have regularity conditions on the initial data that allow it, the convergence will be square root of tau, as proved by Crandall and Liggett, or it can be the whole tau. Okay? So linear order. And before I go into the details, I want to illustrate why this is an interesting and not an obvious result. If you think about this variational inequality, the solution u as a function of time is not very smooth. And when we think about the approximation of the Euler method, for instance, in the ODE context, even if it's written in Banach or Hilbert space, when we derive a linear order of convergence, typically we go through a Taylor expansion that assumes at least 2 orders of differentiability. There is not such a thing here. So the fact that we are able to do the theory is because we are going to compensate. We are going to compensate regularity with monotonicity, and that's where the key things or the important new ideas come from. So keep in mind, this is the energy dissipation that will play a big role. And so how do we do the analysis? Given the fact that I have these values at the time steps, un minus 1, I interpolate. And I create a function, capital U, which is a linear function, piecewise linear function in time, joining the values un and un minus 1. This function now is continuous in time. I stick it into the variational inequality. Okay? And of course, I don't get less or equal to 0. I get a measure of how well this capital U satisfies the variational inequality, which is here on the right-hand side. Okay? I call that a residual. You see, it depends on the solution, the continuous the discrete solution un and this interpolant. So this quantity in red will be important for us. Okay? I want to estimate this residual. So in order to estimate the residual, one important difficulty is that here we have phi of u. U is convex, but it's not smooth. I'm not assuming smoothness. I'm assuming convexity. Okay, for instance, for the obstacle problem, the phi contains an indicator function, which is certainly not smooth. So the remedy to account for the lack of smoothness is convexity, and so I'm going to replace the phi, because of convexity, by the values at the ends, un minus 1 and un. No regularity involved. So that is an estimate for the phi here. Then you put it together, bring it here, collect powers of t, and you get that RT is Tn minus T, so it's order tau n times the En, which I mentioned earlier, the energy dissipation that I mentioned earlier. Okay? Then you look at the error equation. In the variational inequality for small u, you take capital U as a test function, and do the opposite in the discrete variational inequality, satisfied by the piecewise linear function, capital U, you take as a test function small u, okay, and add up. When you do that, you get this error relation. The derivative of the norm square is bounded by r, which I told you earlier was this. Now you integrate. You see, it's very elementary, integrate in time, and you get this relation. So the max of the norm in the Hilbert space square is bounded by whatever you do at the beginning. Let's assume it to be 0. And this energy dissipation, and there are no constants involved. Constant 1, constant free estimate. Okay? It turns out that you have a discrete version of this energy, this dissipation inequality. I wrote it here. Is by playing with the discrete variational inequality at the previous time step. So naturally, from the discrete variational inequality, you get a discrete version of that. And combining this and doing a very simple manipulation, which is here, I'm not going to get into the details, you start from the En, which is the quantity that I mentioned is a key in terms of phi, and you can rewrite this by something larger that involves the f. In fact, a quantity that involves f that will appear later. So you see here, you get, well, I wrote it after actually here, you get the difference of f's times the difference of the u's. So this is not an obvious estimate because it combines regularity. You see, typically we are used to having f alone of u alone in the estimate. This is a combination of the two. And it's an upper bound for the epsilon n, if that makes sense. Okay, so here there are some couple of results which I mentioned earlier. So what I mentioned here, this one, a couple of estimates, one involving epsilon or involving d, and if you go back, this is the result. The question is, how good is this? Is this any good? And here is what you can see. If the initial data, the discrete initial data, happens to be in the domain of phi, then that quantity that measures the error is controlled by the value phi of u naught times the largest time step. Okay? So if you take the square root, this would mimic the Crandall-Liger result, when the regularity of the initial data is to be in the domain of the functional. If the initial data happens to be in the domain of the subdifferential, it's a stronger regularity. For the obstacle problem, this would be the initial data being in H1. This would mean the Laplacian is in L2, in addition to the u naught being in H1. Then this quantity, again, that measures the error, can be bounded now by this factor, again with a constant 1/2, times the time step square. And then you get to this estimate with a linear order. And that, again, doesn't involve any regularity beyond this for the initial data. Okay. All right. Here are the convergence proofs for this rate, a priori rate. The proof is not difficult, and it's based on, let me take this assumption, let me make this assumption, eliminate the difference at the initial time. It comes from the fact that En is bounded about by the difference of the potentials. So the potentials have a natural order because this En is non-negative. So then you can sum up, you get a telescopic sum, and this is bounded by the initial value, and that's it. Okay? That leads to the estimate that I mentioned before. And for a strong regularity estimate, you need to do a telescopic cancellation involving the F, which is written here. The details are not relevant. It's a similar telescopic cancellation, and you end up with the regularity of the initial data. So it's a very simple calculation. If you have a right-hand side F, it's a little more involved, and I'm not doing it, but this is the essence and why it works. And here are some examples, going back to what I mentioned before. For a parabolic obstacle problem, the estimate, the En, can be written in terms of what I call Dn, and you get the difference of the consecutive discrete solutions in energy, and then this mixed regularity that involves this quantity Zn, okay? Which is a very non-obvious thing if you think about it ahead of time. This controls the error. For the degenerate parabolic equation, this is the Dn that controls the error. You see the product of the betas for two consecutive solutions. Remember, the beta is that. In the language of Stefan problem, this would be the temperature multiplied by the difference of enthalpies, which again is not an obvious regularity involved because it's a mixed type involving both variables, temperature and enthalpy. And if you happen to have an initial condition for the Stefan problem that is in H1, the temperature is in H1, which is a natural assumption, then you get linear order of convergence, which is a non-obvious statement for the Stefan problem. Okay, and here you have the example of the TV flow, which I rewrote, remember, as a system in terms of the variable z, whose divergence is in the subdifferential of the total variation, and that is written here. This comes from earlier, for the earlier discussion. The discretization in time, again, is a system, an obvious discretization for that, and here this is the discretization of the variational inequality, very much in the spirit of what I discussed yesterday. Okay, how well is the pair UN-Zn doing? Well, here you have the results a priori. If the initial condition happens to be BB, which is a natural assumption for this problem, then you get a square root of tau convergence rate. If the initial condition happens to be in the domain of the subdifferential, which is a very non-obvious gadget for the TV flow, it's a very rich convex set. It's not obvious what this means, but if you happen to be, then the rate is linear. Okay, you see tau squared here because we have a square of the norm. Again, this is an application of this abstract theory, but if you think about going ahead and doing it directly for this type of flow involving the functional total variation and the z, whose divergence is in the subdifferential, how to get an error analysis for a time discretization is a very non-obvious proposition.
Can I ask a question? Sure. If you go back 2 slides.
2 slides, here.
On the bottom. This is the one with the constraint, the obstacle problem, and then you have the calligraphic F.
Yeah.
Does it contain any information about the obstacle?
Yeah.
Okay. Okay.
Yeah. It's implicit for the obstacle problem. That is buried into this z. which is written in terms of the Laplacian of the solution and the time there the information of the indicator is hidden.
And then there is this tau, which is the time step, yes?
Yeah.
How come that it doesn't get worse if you go further in time? So you always have a uniform in time?
No, the tau is the tau is variable. It's not fixed. Tau is variable. And for this problem, without forcing, the behavior does not get worse in time.
Yes, that's what I'm wondering.
Well, this is a parabolic problem, so there is a regularizing effect. This does not get worse in time. Of course, if you have a forcing, which I ignore for simplicity, then things can be driven by the forcing term, and that is a different situation. But I avoided this in the discussion. So it's natural that the time doesn't deteriorate things. This is not hyperbolic. Okay, very quickly, the theory goes further. What I talked about before are problems that are subdifferentials. It's a potential theory. You can go away from potential theory and talk about angle-bounded operators. This notion of angle-bounded operators goes back to Bresis. Caffarelli rediscovered this later. I think called this something like epsilon monotone, if I remember correctly. Anyway, here is the definition. If you want to do an error analysis, and these are the equations, you take the difference and multiply by u minus un, and you get this. So now if you split the right-hand side in a way to exploit monotonicity in this term, you end up with this red term, which is not obvious how to handle.
I don't understand. What is capital U sub n in this slide?
Well, it's related to what I defined before. Capital U sub n are values of a discrete solution at times Tn. And capital U without any subscript is a piecewise linear interpolant. Okay?
Yeah.
And I'm ignoring the residual here because it doesn't matter for the discussion. That should be in this equation. In order to get an estimate, you have to handle this term. And here is the assumption. If you have this, the operator is called angle bounded. You see the un takes the place of v, the u takes the place of w, the u takes the place of w, and the z is the un. And you want that this quantity is controlled by a parameter gamma bigger than 0 times the difference of f's and the arguments only v and z. So the middle argument goes away. Okay? This idea goes back to Bresis. If you have this type of operator, then you can do the same thing I mentioned earlier. Here is an example. You can have an operator that has convection now. Okay? And if you go through the theory, here are the results that you get. This in the middle comes because of coercivity, which I ignore in the discussion. And on the right-hand side, you get the estimators, okay, that involve differences of values of u, capital U, just written this way. So this is an upper bound, and this constant free, as you see, for an operator of that form. You can have an obstacle associated with this, which would be important, for instance, in applications in finance, where this term is a drift term that is important in the applications. And the same theory will go through, as I said before. Okay? This problem is still parabolic, okay? Even though we have a convection term, this is dominated by the diffusion, and that's why, even though we don't have symmetry, this is not a potential problem, it's still a diffusion-dominated problem. And you see that things get worse in terms of gamma if the nu is small relative to the convection, which is what you would expect. If the convection is dominant relative to the diffusion, then things tend to blow up in this theory. Okay. Now, space discretization. Okay. So here I'm going to explain this sort of abstractly. Let me assume that now I have in space an approximation of our Hilbert space, which I call H sub H. H is a parameter like the mesh size. This is a finite dimensional subspace. Say, think of finite elements as I discussed yesterday. Associated with this finite dimensional space, I have a functional phi sub h. That could be the original functional, simply restricted to h sub h, or it can be a modification of the functional. That's why I put the subscript h. But with some assumptions, okay? A monotonicity assumption, okay, which is written here for every element in the discrete space. An approximation assumption. So given a space containing the domain of the operator, densely contain a space of smoother functions, think of C infinity functions, then we can approximate any element in this space by a discrete object, Clement type, that's why they call it C sub h. This is a discrete object with some rate of convergence epsilon 1. And then there is an energy diminishing property. So if I replace any element W by the corresponding approximation and the discrete functional, I don't increase the energy too much. If this happens to be 0, then will be energy diminishing, but we allow a little bit of an excess by going to 0 with h. I call it epsilon 2. Okay? A perfectly energy diminishing approximation will have a 0 on the right hand side, and I will say a couple of words about that later. Okay. Then here is a semi-discrete problem, which I mentioned earlier, and I discussed the error estimates for you before. And this is a fully discrete problem. I put h's everywhere. So now the functions uh, uk, well, this should be n, sub h, and the w's are discrete. And we can even allow a right-hand side with the function rho, which is convenient for inexact solutions, which is not important for the discussion now. Think of this rho to be 0 if you do an exact solution. In practice, you don't do an exact solution. You will do an iteration. We want to control the role of that iteration. There is an error associated with an iteration, and I hide that into the rho. Okay, here is the theorem. If you happen to have this function in the domain in the space W, you have a bound for this rho in time and space. Then this is the error estimate. As you see, it depends on how well you approximate the initial data, and the epsilon 1 and epsilon 2 control the error. This tau here comes from the approximation of the rho, which you may think to be 0. Okay, so that's the result. It's an abstract result. How does it work? Let me be precise now with an example. How does it work for the TV flow? Well, this is the discretization in time. But I told you that I will not be using this discretization. I would be splitting the discretization of the TV flow into a system where I have a variable z and a variable u. So this is the equation for u, where I have a z in the unit ball of the space x that I introduced earlier. And this is the equation, the variational inequality for z. Okay? Now, if you look at this formula, this looks okay in appearance. It looks like a discrete formula. But this is not, this object here that you get out of this variational inequality is not really a discrete quantity. It's not in the space. It's wherever it satisfies this variational inequality. The fact that there is an h here is because it's associated with a function that is discrete. But the object itself is not discrete. So this is not enough. This is the first step. We have to go further to get a method that can be implemented, and then we need to know how to solve it. I'm not going to discuss the solution of this. This is another topic, and we have a method following ideas of Chambord. But this will not be part of the discussion. It will be too much for today. So how do we do something here that will lead to a practical method? So I had to replace this variational inequality by something else. And in a couple of words, this is what is done. I replace the functional phi by a quadrature. Okay? For instance, if you have triangles, we are integrating at the we are using a trapezoidal rule. So we use the integration at the vertices. If you have triangles, we also use a trapezoidal rule type of, we use the four vertices of a rectangle. Okay, and that leads to a formula for the computation of an integral of the gradient. So this is an approximation of the total variation of the function v, h, in this discrete space. But it now has only 4 or 3 degrees of freedom depending on what you do. With this, which is an approximation of the true potential, and the reason why I wanted to get away from the true potential and have something that is discrete, but not too far, then we have the properties that I mentioned before. We have the monotonicity, which is a consequence of convexity. We have approximability, that has to do with knowing, given a function in BB, how to approximate it. This is not a simple thing. You first smooth it out by convolution, and then you approximate the convolution. It's not completely trivial, because if you have a function in BB and you convolve it, you need to know what to do with the function near the boundary, because the function is not defined outside the domain, but a convolution would need a little bit of a function valued outside. So you need to extend the function. But if you extend the function, you may lose a little bit of the approximability. So there is a point here. You need to extend the function with a constant for the extension that is close to 1. And then you have an energy diminishing property that is written here. Again, this has to be calculated. So you have the 3 properties that I mentioned, and then you can go and have the result. So this is the result for the TV flow, as I mentioned. But you see, because of the lack of regularity in time, this is a bad problem in many ways. This is what you get for the dependence in h. Okay, you get h to the 1/6, which is a kind of depressing result. But that's what it is. If you happen to have a TV diminishing interpolation, meaning this, given a W, you can construct an approximation of W whose TV norm is bounded by the TV norm of W, constant 1. If you can do that, this rate gets to the power 1/4. Again, by looking at the proof. And if you use these ideas in the context of total variation minimization, typical of image processing, no time in this game, having this operator will lead to an order h to the 1/2 for the TV minimization. And for this context, h to the 1/2 is an optimal. It's an optimal rate of convergence. Okay? If you have a function in BB which is bounded, the best you can say is that it's in a best of space with regularity 1/2, and that's why you get a 1/2 and nothing more. If you measure the error in L2, which is what we are doing. We are not measuring the error in L1. Remember, this is a Hilbert theory. Okay.
Can you read such approximation?
Well, this is a tricky thing. It's a tricky thing. Can we make that such an interpolant? Well, this is a very delicate construction. The construction is not difficult if you allow here a constant. This is okay. But if you want the constant to be 1, then it's not obvious. And here is a construction, which is not true in general. Say, I plotted here rectangles, but you can have right triangles too. Okay? Imagine that this is cut with a diagonal, it would be okay. So given a vertex, you look at this patch in blue, okay, which covers exactly 1/4 of each of the rectangles. So this patch, in this patch, which I call Q, you integrate your function, and then you get the value which I call W sub z, associated with the vertex. Well, I call it V here, I call it Z here. So this is a quantity, this is a constant. So now you define an interpolant which at this vertex is equal to that mean. And then you connect with bilinear functions, which is a very simple construction. If you do this, then this operator has the property that I mentioned of being TV diminishing with constant 1 and some other properties in other norms. Okay? The proof is tricky. It's not a standard interpolation estimate because we want constant 1. And then you also have approximability. For instance, you have second order. It's kind of strange because if you look at the construction, I'm projecting over constants. How can I get second order? Because the construction is very symmetric. If your function happens to be a linear and you do this construction, the value that you get here, which I call WZ, is exactly the value of the function, of the linear function. So by symmetry, even though we are projecting on constants, we get that we can resolve linears. And that leads to second order approximability. Anyway, that's the answer to your question, but it's not an obvious statement. Okay, so now let me show a few simulations to get some intuition about this flow.
Projection is constant and linear.
No, the projection is a linear, but in this case it's piecewise bilinear. So this way I define the value at the vertex. I will have another value here and at the other 4 vertices. And then you connect with the bilinear. Bilinear means linear in each direction. Okay, that gives you a bilinear function. And because I'm enforcing the value at the vertices, you will have continuity, naturally, in the whole domain. If you have triangles instead, so think of having the diagonal here, you will have piecewise linear functions that will be continuous. So, to elaborate a little more on your question, you may wonder what happens if we distort this mesh a little bit. What happens, for instance, if the triangles are not right triangles? And what we prove is that if this operator happens to be there, this is a theoretical tool. It's not something we need to construct. But theoretically, we prove that the TV diminishing flow, this result here, we prove that there must be order 1/2 convergence. Okay? If we distort the mesh, we check numerically, and the order is not 1/2. Okay? So that tells you that if you have a mesh which is not as regular as I suggested, there isn't such an operator. So it's very, very special construction. Okay, so here are some of the examples. This is a characteristic of a circle. Okay? And you have an exact solution. In particular, I want you to see, because it's a very non-obvious. Okay, so this is the characteristic of a circle. So you see this wall is falling down within one element, and I want you to see what happened with the simulation. Okay. Okay. So you see the characteristic goes down, but there is no diffusion.
But the equation is conservative at the beginning. It's ut equal u this TV flow.
Yeah, it's ut minus the divergence of grad u over mod grad u.
So it's conservative.
Yes.
You cannot you lose mass.
Well, here I have the initial boundary conditions. I don't have Neumann boundary conditions. For conservation, I would need.
But you don't see them.
No, well, yes. Yes, but in any event, this is what the flow is. In fact, if you this is an exact solution, which is the characteristic falling down with a certain speed dictated by lambda. Lambda has to do with the radius. This is the exact solution. What I wanted to illustrate the fact that the numerical method, this is computed with the method that I just mentioned, does not have any diffusion. And does not have any regularization. There is no regularization for this calculation, and you see that the walls remain walls within one element. This is an interesting feature because this type of functional is used, for instance, in problems where you want to preserve edges, like in image processing or in material science. And this preserve edges, this doesn't round the edges. So it's a good feature to build in a method, a numerical method, that sort of preserves one of the main features for which the flow was introduced to start with. Okay, so here you have a problem with boundary conditions that are Neumann type. but I will put a forcing term, a constant forcing, and I want you to see. You may now suspect what's happening. I don't know. So here is the flow. The forcing is such that it keeps the top of the characteristic fixed, but the bottom goes up until it joins. There is no diffusion again, as you see.
F is constant?
F is constant. The right-hand side is constant.
It's a constant in X.
It's constant in X and anti. So it's pushing the whole thing up. Okay. So here you have the example of a disconnected set. This is form of three circles, and these are the characteristic functions of the three circles. Okay. So let me show you what happened. So depending on these circles are actually the centers of the circle are at the vertices of an equilateral triangle. It happens that, so this is the situation. So here you have the circles. There is a relation between the radius of a circle and the length of the triangle, which is the size, which is equilateral, for which the cylinders or these sets don't see each other, which, as you see in the picture, and the behavior of each of these characteristic functions is what you saw at the very beginning of one characteristic function. If R is large relative to L, and there is a formula for that, then they will see each other and there will be interaction, which is not this case. Okay, and here you have another interesting situation. I hope you can see. This is an annulus, so it's cut in the middle. So it's an annulus, and you have a characteristic function of it. So in the middle, in the center, is 0. Okay, so it's two circles. This is the situation. So you have an interior radius and an exterior radius. And so the characteristic function of this set is what is plotted here. And here is what happens. So you see the top is going down, but also the interior is going up, which is a very reasonable thing to diminish the jump that quantifies the total variation. And when these two meet, then it goes down, as we saw before for one circle. Okay, all these examples are academic examples because we know the exact solution, but this was useful to control the error and see what the decay is. We observe a decay better than proved by theory. We observe h to the 1/4, but we cannot prove that. Have some ideas why it's the case. We don't have h to the 1/2. Okay. The last comment I want to make is a connection between this and the so-called regularized TV flow, which is written here. If this epsilon is not there, is what I told before, and the method that I discussed is designed to work without epsilon. But if you write an epsilon, now this becomes a parabolic problem called regularized TV flow, and it has been used to compute because now it's parabolic. But of course, it's not well behaved because this epsilon is supposed to be small. In particular, using this result, which goes back to Feng and Prohl, that is an approximation of u by u epsilon being the solution of this problem, and our results on interpolation, it's possible to prove this error estimate, which is new. This being the discretization of this problem. Okay, that's why I call it epsilon h. But how these two things compare? I want to illustrate that with this picture. This is a situation where the initial condition, which is this function, this, let me call it ramp function, in one dimension, is supposed to be stable for TV flow. If you have something monotone like this, the TV flow should keep it. There's no way you are going to change or improve the total variation by changing this function. So it's stable for the TV flow. If this is the initial condition, the TV flow will keep it. And that's what happened with our method. This in red is a solution of our method. And these are solutions of the regularized TV flow for different values of epsilon. This is for an epsilon which is not that small. I don't know, it's written somewhere. It's ordered h, and the other is ordered h squared. So you see, you get better if epsilon is smaller, but eventually there is a deviation from the true value depending on the size of epsilon and how long you wait. If this is an important aspect of your application, then going for something that is avoids regularization may be a good thing to do. However, you having a regularized flow is important in several respects. It's simple to compute, simpler to implement than our method, and can be used to initialize our method. Okay, so there are still value of this regularized flow. Okay, I wanted to conclude to link with the discussions of yesterday by Benoit Pertam and something I will say tomorrow with the Allen-Kahn equation and connections with these ideas of gradient flows. So this is very quick. So here is, in one transparency, a very quick view at Allen-Kahn. So the underlying space, Hilbert space, is L2. I'm taking an inner product in L2 which is scaled by epsilon. So this means basically a rescaling in time. This will define the scalar product for the gradient flow. So rescaling in time. The functional is this, contains the Dirichlet form, and this quartic nonlinearity that has two minima at 1 and minus 1. Oh, this square is supposed to go out. F is the derivative of that, which is a cubic, and then this is just the gradient flow. The derivative in time in this measured in this with this norm is equal to minus the derivative, the subdifferential of this functional, which is this. Okay, and that's Allen-Kahn. Scale in the way that is convenient to see mean curvature flow. Okay, so this is the equation. It was introduced by Allen and Kahn. I don't think they were thinking about gradient flows. When they did, they were thinking more about problems in materials. This is sort of a mathematical interpretation of the equation. Now, if you want to do an error analysis, very much in the spirit of what I discussed earlier, the first thing you notice is that this functional, this is convex, but this is non-convex. Okay, it's a quartic. However, it's ellipsis perturbation. An ellipsis perturbation can be handled within the theory. But of course, in order to do that, you will have a behavior that depends on the ellipsis constant relative to the underlying norm of the space. The ellipsis constant happens to be 1 over epsilon squared, because I have an epsilon here. If you move it down, it will be 1 over epsilon squared. So the theory works. You would get an error estimate the same way I discussed before, a priori or a posteriori, but there will be a constant which is exponential in epsilon. So for as long as epsilon doesn't go to 0, this is a meaningful result. If epsilon is tiny, either because you are really looking at the problem that is faithfully mimicking the materials, and epsilon is a length, the thickness of an interface, which for a domain of size 1 can be several orders of magnitude smaller, 10 to the minus 5, 6, depending on the application, then this is not a meaningful result anymore. If epsilon is going to 0, this is not a meaningful result either. And then you wonder, well, what is the value of this? It's certainly very appealing computationally because it's a parabolic problem, it's smooth, so you can discretize it and compute. But in order to get meaningful results that had to do with the limit of the problem, mean curvature flow, as was mentioned yesterday, when epsilon goes to 0, what happens is that this is certainly discussed in several contexts, but using gamma convergence by Bellettini, Paolini, and Verdi some years ago, that for the stationary case, if this is epsilon, the size of the thickness of the interface, the parameter h has to be small o of epsilon for convergence, which means that in the transition region, there have to be many elements, asymptotically infinitely many elements in the cross direction. For the computations, a rule of thumb is that we need 10 to 20 elements to resolve the layer. So if you go and do computations using uniform meshes, and your epsilon is tiny, several 10 to the minus 3 or 4, then this requires a lot of degrees of freedom in the whole domain, where the action is only taking place here. So the use of adaptivity and mesh refinement is critical. So I want to say a couple of things about that and conclude. And what I'm going to say is related to work by Feng and Prohl in the regime what is called sometimes developed interfaces. I think this was introduced by De Montoni and Schatzman in their work on asymptotics on this. If you start from an initial condition that is not well adjusted or prepared for the front, there will be a very quick rearrangement in time of the order epsilon square, where the function u, whatever it is, will become like a prompt. -1 somewhere, +1 somewhere else, and a transition. Okay? If you start with that front already, so you have a well-prepared data, then this exponential is not there, and you have polynomial behavior in powers of epsilon to the -1. Well, this is a result that is very interesting, and it's based on asymptotics. It's a rigorous result based on asymptotics by De Montoni, Schatzman, and Chen. Now here is a posteriori version of it, which is useful, as I mentioned yesterday, if you want to do adaptivity and know how to refine this region without refining the rest. So you need estimators. So how do you do that? So this is the equation again. This is the discretization in space and time. You do a linear reconstruction by joining the values of un and un minus 1 at the nodes. As I mentioned in the error analysis earlier, you write the residual, which is you plug this u into the equation and see what happens. And whatever it is, you call it R. This is a defect measure, let's say. If this R is 0, then the capital U is a solution, which it isn't. So this is R is not 0, you have to measure it. But it's computable because it depends on the capital U. Then you go ahead, do it. Use this spectral estimate, as I said, goes to the Montoni, Schatzman, and Chen, that had to do with the behavior of the solution for a well-prepared initial data. You already start with the front. If you go through this and you assume some relations, you get a tolerance that you want to meet, and then you, by making some assumptions on the estimators and the initial data, you can see that you can achieve that tolerance. So I wrote this in terms of tolerance because it's rather technical. What you have on the right-hand side are the estimators for time and space, which I'm not describing, and those are in turn bounded by delta, which is in turn bounded by epsilon. So you can get an a posteriori theory like this that has been extended very recently in several directions by Bartels. So this gives you a very quick, I hope, but still meaningful view of gradient flows and some applications. So with this I stop. Thank you.
For this constant that exponentially grows, what is the norm of the error in space that you consider?
It's a natural energy.
I mean, if you
It's a natural. You are talking about this one, right?
I mean, because the limit is not in this space.
I know, but that's one of the problems. But there is no error analysis that I'm aware of that would measure, for instance, the error in BB or the error in L1. In time, the measure is in L infinity L2, and in space is in H1, L2 H1, with proper powers of epsilon. But the behavior is exponential. And since you ask, let me make a further comment. Is this there? Or is just a problem that has to do with the theory that is not well adapted? This could be a problem. The analysis that we have is not sharp enough. This is always a
I
problem.
mean, the limit is not in that space, so
I understand.
we should do it.
Well, but should it blow up like this? There are many ways it can blow up. What I want to say is that if you don't have the Laplacian and you only have the logistic ODE, which would be this, and you start from an initial data which is not well prepared, so something between -1 and 1, the logistic ODE will not see space, it will only see time. Things that are less than 0 will go to -1, things that are bigger than 0 will go to +1, and the time interval of that is epsilon squared. This is an exponential behavior, a transient, and that is accounted for by this exponential. So the exponential behavior is there. So if you don't make assumptions on the initial condition, which I did, I assume that it was a developed front, you cannot do better, because this is what you expect for ODEs. And the space variation is not going to help you in this initial transient. Okay, so if you have a well-prepared data, because you care about approximating a problem where you already know the position of the front, then you can get around this. And that's the value of this analysis.
No more questions? Thanks.